Our next speaker is Shalini De Mello. She is a Director of Research, New Experiences at NVIDIA. She was also Distinguished Research Scientist at NVIDIA. Her interests are in AI, computer vision, and digital humans. Welcome to Illinois, Shalini. There's yours.
Hello, everybody. So today I'm going to be talking about an interesting problem, which is on open vocabulary recognition with large text-to-image foundational models. And in the context of this, I'm going to be talking about both clip-style contrastive models as well as coupling them with generative models, which is sort of the theme of this talk. And so I got interested in this open vocabulary recognition problem once we started seeing these really large models emerge that are trained on internet scale data, which is both clip as well as diffusion-based generative models. I saw this as a path forward to being able to scale recognition problems to a large variety and diversity of classes. And that sort of sets the stage for my talk today, and that's going to be the theme. And so I'm going to be basically focusing on trying to explore how we could use these large models, vision models that are trained on very large corpus of data to achieve open vocabulary recognition. So before I go into the specific works that I'm going to describe, I'd like to acknowledge all my collaborators, primarily from NVIDIA, as well as from the University of San Diego, that is Xiaolong and Jari, who was a very active and very smart intern we had at NVIDIA, who worked on two of these works that I'll be describing. All right, so in the computer vision community, we've had amazing data sets that have pushed our field forward. We've had ImageNet that has helped to move the recognition of object recognition problem a lot forward, but that required a lot of effort to collect and curate the images with the right labels and so on and so forth. We've also had the COCO data set, among others, for moving forward the field in object detection. We've had the Pascal data set and Pascal context data set to move the problem of pixel level labeling, which is semantic segmentation or other forms of segmentation, panoptic, et cetera, forward. And then we've also had this Flickr 30K data set where we've had referring expressions related to describing contents and images that have also helped to move our community forward. So all of these have been very, very great. However, one problem is that they tend to be quite small in terms of the categories, relatively small compared to what exists in the world and the number of categories that are represented or things that are labeled. And they require a significant amount of human effort to collect and curate these data sets, whether that be for just labeling category labels or semantic segmentation, which is probably the one that's hardest to label because it takes a significant amount of annotators' time to label things at the pixel level. There's many tools that have been developed over the years to improve the time that's required, but nonetheless, this I would say is one of the hardest things and time-consuming things to label, which is semantic segmentation labels for images. So on the other hand, we have, besides these really highly curated and clean data sets that have very small closed vocabularies, we have a lot of text on the internet, which comes with weaker caption labels. So oftentimes, there'll be in websites, there'll be text that describes images and has captions for them. But what this comes with also is the fact that these captions may sometimes be completely irrelevant to the images or the content of the images, but we just have a lot of this data. So it represents a lot of diversity, both in terms of intra-class variation, as well as a lot of classes and objects and concepts that are described. So how can we sort of use this data to be able to do recognition beyond small closed vocabularies, which is kind of the question that we were trying to answer. So related to that, the first work that I'm going to describe is a work called Group VIT, where we showed that semantic segmentation can actually emerge from weaker text supervision, like, for example, the caption supervision that comes with a large amount of internet scale data. So this was work we published at CVPR 2022. So around the time when we were thinking about this, there was some really nice prior work. There's been work that showed that, you know, when you try to predict when you try to do the captioning task, you can actually use those models to do object detection with them. Similarly, on the right, there was the CLIP paper that came out of OpenAI around that time, which showed that the CLIP model, because it was trained on a large amount of data, had very good zero-shot generalization capabilities for the task of object recognition. So this kind of inspired us, and it got us thinking, well, can we actually sort of do this zero-shot recognition task at the pixel level, which is for semantic segmentation? So is it possible to even do zero-shot semantic segmentation is the question we asked. So what is zero-shot transfer to semantic segmentation? So here the idea is that oftentimes when you train a model for semantic segmentation, you have these ground truth labels available. They could be ground truth labels for a closed set of classes or the classes that you care about. Typically, for the best, largest labeled data set, we have about like 100 or to the, maybe 200 classes labeled. That's the typical way of doing it. As compared to this state-of-the-art methodology, what we wanted to do is, let's say we have no labels whatsoever of any classes, segmentation labels available, then completely mask-free, can we input an image into our model and it produces some sort of segmentation mask for the objects in the images. So for this, we proposed a model that we call Group VIT, which is basically a modification of the vision transformer VIT with a bottom-up hierarchical grouping, which is what I'm going to describe next. And what we found is that with this model, we're able to actually allow this bottom-up grouping or segmentation to emerge simply using weaker text supervision from captions alone. So in Group VIT, the idea was that during training time, you have a bunch of images with their captions available, and we trained the Group VIT model with a contrastive loss, just with text supervision, which is caption labels. And the Group VIT model learns to do this bottom-up grouping and segments emerge. And then during inference time, whenever you have a set of new test images, you would use Group VIT, which would then produce the segments. And then we would compute the similarity of the segments to a open vocabulary of object categories and associate the embedding of the text of each class to the representation from each group from the image to categorize them. So let's just quickly look at how what enabled this Group VIT architecture. So in the VIT architecture, as you all might be familiar, we divide the image up into non-overlapping sections. That's what we do as well in Group VIT. But what's different in Group VIT is that in addition to the image tokens that are input after a linear projection, we also introduce these learnable grouping tokens. And these learnable grouping tokens, they go into a transformer block and then a grouping block. And the idea there is that if we kind of look more closely at the grouping block, the idea is that the spatial tokens get assigned to one of the grouping blocks. So essentially, the grouping block is kind of doing this function of, sort of clustering the spatial tokens in a semantic manner. And so we find that with these grouping tokens, some groups emerge and are learned. And we have another stage. So this is like the first stage grouping. And then we have another stage of grouping where we further combine these smaller groups into larger groups together. And all of this is together learned with a contrastive loss, which is coming from the text supervision. And the key to making this loss work was that typically in a clip-style model, you would just use a contrastive loss with the entire text of the sentence or the caption encoded. But here we introduced additional contrastive losses with the individual nouns that were present in the caption as well. So that was one key component to allowing these individual groups to emerge. So with that, as I described previously, once we had trained our model, we could use the group VIT model. The encoder, the image encoder would produce the segments. We would then get the visual representation from each segment and match it to the text representation of an open vocabulary to then classify them. So we also tried various other ways that are sort of logical ways to try to try to create segments in an image. So you could do, for example, you could try to match the text in a pixel-wise manner to label each individual pixel in the image. You could do k-means clustering of the clip representation, internal representation of the clip model coming from the image encoder. You could do mean shift clustering of the clip model, or you could do spectral clustering. So compared to all of these, the segments that emerge using group VIT, which is our modified architecture of VIT, were significantly better. And also, we also tried a number of different representations that could be or self-supervisedly learned or supervisedly learned representations that could be transferred to the task of segmentation, zero-shot segmentation. For example, using a supervised DIET model, which is trained on ImageNet with labels, or a Dino model or a MoCo V3, both of which are trained using self-supervision. And we found that using this text supervision in group VIT significantly helps versus using just purely self-supervised models, as comparable to this fully supervised model. Also, interestingly, we compared how this group VIT model, which is a slight modification on the VIT, would do for the task of object classification or image recognition versus like the vanilla VIT. And we found that for downstream zero-shot image recognition tasks, it performed equivalently. So it didn't lose any accuracy for those tasks as well. So finally, I show some results here. So what you see in the second column are the results of the first stage grouping. And in the third column is, following that is the results of the second stage grouping. And then that's the final prediction compared to the ground truth. And this is on the Pascal VOC data set. Here are some more results. And we also have some results on the Pascal context data set. And so to conclude, what we found was that it is possible to hierarchically group these visual tokens into irregular shaped semantic groups using text supervision alone. And we can successfully also transfer these to new categories that haven't been encountered at all during training. You can generalize to a lot of different concepts in the world, but without any fine-tuning. But the segmentation quality, as you may have observed, is quite coarse. Part of it comes from the fact that we use a VIT architecture, and in the VIT, if you have a large number of tokens, which is what you would want to have for a segmentation task, you run into the problem of requiring a large amount of memory to store sort of a large number of tokens. And the other thing we noticed is that the association of each segment to a particular text or particular category is done through similarity with the text encoding with a clip model. And we found that to be quite weak. And part of that is because clip is trained with a lot of noisy association between vision and text. So to go further, we then this year at CVPR 2023, we proposed a new model for open vocabulary panoptic segmentation called Odyssey with text-to-image diffusion models. So in this particular work, what we were trying to look at is, well, can we do open vocabulary panoptic segmentation? So compared to the previous work, we made two changes. The first was, instead of just looking at semantic segmentation, which looks at just foreground objects, some panoptic segmentation involves the segmentation of stuff or amorphous objects in the background, as well as instance segmentation of foreground objects. So we're looking at both things. And secondly, what we decided was we wanted to use some segmentation labels if we had any. So the previous work, we said, OK, can we just not use any? But here, we said, OK, we're going to use labels that we have for a closed set of categories that we have available. So we were inspired by diffusion models. We know that diffusion models they're able to produce really good images based on text conditioning. So if you look at kind of like the cross-attention layer of diffusion models where the text conditioning is applied, clearly, there's some supervision being provided from high-level semantic concepts into individual locations, pixel locations. And the fact that diffusion models can produce these really nice boundaries, kind of semantic boundaries, indicated to us that their internal representation space must be fairly well differentiated semantically. So we looked at k-means clustering of the internal representation of the diffusion model space. And it kind of looks like this, which looks pretty well differentiated. And when you compare that to the internal k-means clustering of the internal representation space of a clip model, the encoder of a clip, image encoder of a clip model, which is on the right, you can see the differences, that it's not as clearly well defined as the diffusion model spaces. So this inspired us to think about whether we could use the internal space of these diffusion models to do open vocabulary panoptic segmentation. So we proposed this specific model for it called Odyssey, which I will describe next. So this is how Odyssey works. So when you're given an input image, and this is during training, so one of the things, we try to input this image into the diffusion model as the first step to extract its internal representation for the diffusion model. So one thing we realized was that diffusion models, they extract the best representation from real-world images when they come along with a caption, because that's what diffusion models are trained to do. You always have a text caption, and then that's how you denoise and produce the image. So what we do is we have a real-world image. We add a small amount of noise. We found that using sort of the last stages of the diffusion process to add a tiny bit of noise is enough. And we needed to create a caption for this image. So we tried multiple things. You could take the image and put it through blip2, for example, to produce a caption. And we tried various things. But in the end, what we found worked best was you take the image, you pass it through the image encoder of a clip model, and then on top of that, you have a small trainable MLP that kind of acts as a transformation layer, which is learned. And this creates an implicit caption for the image. So now with this implicit caption and the slightly noised image, we input that through a frozen diffusion model. And we extract the internal features. This is a stable diffusion latent model. And we extract the internal features of the stable diffusion model from various layers. So we had some features from the encoder, some from the unit, and then a few from the decoder. So we upsample these features, get them all to the same size. And then we feed them into a mask generator. In our case, we use the mask-to-former model, which is, at the time, was a state-of-the-art model. Alex was also part of one of the authors in that work for doing panoptic segmentation. So with this mask generator model, it produces mask proposals. So in our case, we produce like 100 proposals and also mask embeddings for each of those mask proposals, which are visual representations of the content in those masked regions. And the key to sort of making this work was, in this stage, we used the COCO dataset for training. However, we ignored the specific class labels of the segments in the COCO dataset. And we simply treated them as binary segments. That's it. So it's a class-agnostic binary segment prediction. And this we found is an important step. And we're not the only ones. There's previous work, OpenSeg as well. They found that this is a crucial step to enabling open vocabulary segmentation, because you want to be able to predict segments for classes that are encountered beyond what is in your closed vocabulary. And I think a similar idea is also used in the Segment Anything paper that recently came out, which is to use this idea of binary mask prediction. So once we have these binary mask predictions along with their mask embeddings, we then, during training, try to associate them to the text embedding of the category labels that are available during training, or to a caption that may be available, either using a cross-entropy loss or using a grounding loss. So this is how we sort of train Odyssey on a set of closed vocabulary that is available. And then during inference time, the pipeline is as follows. So we're given an input image. And again, we extract its implicit caption, along with adding a small bit of noise to extract the internal features from a diffusion unit. And then we predict its class-agnostic binary mask along with the mask embeddings. And then so there's one additional step we also do, which is from the implicit captioner, from the end of the implicit captioner, which is basically the image encoder of a clip model, we also extract some pooled features, which are additional set of visual representations for each of the segments that we've predicted. So we get two sets of basically visual representations, one from the diffusion model and the other one coming from the image encoder of a clip model, which is trained up with a contrastive loss. So the reason why we did this was we interestingly found that the diffusion model features are good at producing boundaries, like really nice, sharp, crisp boundaries. Whereas somehow we found that the diffusion model features are not as good as like classifying things. Whereas the clip model's encodings seem to be slightly better at like classifying things. So in the end, we decided to use the visual representations from both of these, from the image encoder of a clip model as well as from the diffusion model. And then when we have the open vocabulary, whatever category labels we have, we encode those through the text encoder of a clip model. And then the text encodings are in the same dimensional space as the visual encodings. We take a dot product between the two sets of visual representation and the text encoding. And then finally, we took a geometric mean to compute the final prediction of the class labels. So here are some results. So how did we do in terms of the accuracy? So we published this work at CVPR 2023, and I think as some speakers previously pointed out, that already seems like a really far time has already passed, although it's just a couple of months back. But at the time, we outperformed both mask clip as well as OpenSeg, which were the two competing methods at the time, by a significant margin on the AD20K panoptic segmentation data set. And here I'm just showing, on the left, I'm showing results of the panoptic score, which is for the panoptic segmentation task, as well as on the right, I'm showing results for the semantic segmentation task. And we have several other results of also doing open vocabulary, bounding box prediction, as well as instance segmentation, which were also all state-of-the-art at the time. And here I'd like to show some interesting results of actually trying to apply this model that is only trained with the COCO dataset to the AD20K dataset for images that it has and categories that it has not actually seen before, several of which it has not seen before. And I think, without having seen several of these categories or trained for specifically these categories, it did quite well. Here are some more results on the AD20K dataset. And as I pointed out in this panoptic segmentation task, it's trying to label both sort of the background things like ceiling and window amorphous stuff as well as foreground objects. And here are some more additional results. And some more. And I will scroll through these quickly. And then we also applied it to the Ego 4D dataset, which is quite challenging and different in the sense that these are all sort of images captured from an egocentric point of view with people wearing the cameras. And in this one too, we found that it worked fairly well. Here's some more results. All right. So the code for both of these is available, and I would encourage you to go ahead and download it and try it, and give us feedback and your thoughts. And I think that's about it, and I'm happy to take any questions.
Hi, thank you for your talk. On the last Odyssey slides, you're displaying both masks and some probability score. Is that a mask confidence, or is that a confidence over the semantic class? Because, yeah, go ahead.
Yeah, that's a confidence over the semantic class.
And how are you extracting that? Because if you're using like some language embedding, right, that's...
Right, so we did have a... So even with like the open vocabulary categories, we do have a softmax in the end. However, so the softmax sort of combines the open vocabulary. So what we do essentially when we do inferences, we append the open vocabulary categories to the closed vocabulary that we use during training. And we try to combine, we produce a softmax score, a probability score across the entire subset of closed and open vocabulary categories. However, they're weighed slightly differently. There's like we found that in the softmax, you sort of have to weigh the closed vocabulary different from the open vocabulary categories. So that's basically how we produce it.
I see. So in practice, you're closing the vocabulary again by just adding,
Just for the purposes of inference, yes. So the assumption is that you do have a closed vocabulary to inference across, yes, in some sense.
I see, thank you.
I had a follow-up question on that actually as well. And like, how do you choose the additional vocabulary? Did you choose those ahead of time, or once you receive an image during inference, can you pick the precise vocabulary that you're doing inference over?
You can pick the precise vocabulary. So in the demo that we have, a user can specify the vocabulary that they would like to append. So for example, or you could even give a sentence like, where is the mushroom in this image? And then we'll pick out the noun mushroom, and we'll append mushroom to the cocoa categories. And so, yeah, you can specify the vocabulary, but it's simply appended to the vocabulary that you saw during training. That's kind of the idea.
Cool, thank you.
Hi, very nice talk. I might have missed this, but could you say a little bit more about how this changes the complexity of the problem as far as training?
So the way that it changes primarily the complexity of the problem in terms of training is that, I wouldn't say it changes the complexity, but it changes sort of the way you train, not necessarily the complexity. So one way is that when you do segmentation, when you're trying to just put boundaries around objects, you do not care. At that point, you sort of do this class agnostic segmentation. And the idea is that you don't really want to necessarily want your segmenter to care about what the particular type of object that it's looking at. As long as it's like some legitimate object, you want your segmenter to be able to produce a boundary around it. And that's one sort of, by being class agnostic, you teach the segmentation model to do that. So that's one thing. The other thing that you're sort of changing in the training is that typically when you're training a segmentation network, you have this final softmax layer where you say, okay, each pixel, what is its category label? And you would have like if you have 100 categories during training, you would have a 100-way pixel-wise cross-entropy loss, right? So instead, you have this additional step where you want to be able to do classification through a clip model, through the encoding of a word into some sort of a encoder, like a text encoder. So that's the other additional piece of it that you change, which is you say that I'm not going to directly classify things into specific categories, but instead I'm going to say whether this pixel or this segment that I've extracted, its visual representation, does it match the textual representation of its category name? So that's the other sort of change that you make to enable open vocabulary recognition. So these are, I think, the two high-level concepts that you want to use during training.
Does it increase the training time very, very dramatically? Sorry, does it increase the training time?
Does it increase the training time? I would say, so in our training, there's two ways of training. One is we use the category labels that were available for each segment in the COCO data set. For that one, not so much. However, the other way we trained it was using the actual captions and a weaker loss, which is the grounding loss. For the second one, yes, it does increase the training time, because there you don't have very direct supervision.
Hi. And another question about Odyssey, which is very, very cool work. Going back maybe to this question of vocabulary, is there, just maybe clarification, is there anything that precludes segmenting categories which are not nouns, but noun phrases or even more compositional? If I want to segment a person wearing a red scarf, can it do that?
I think if you have labels available, yes, you could. So I mean, in Odyssey, we actually used the segments that were available in the COCO data set, right? So as long as people have, human annotators have created or labeled segments like that, I think that's completely fine. The association to the text, if that's a phrase, I think that's entirely possible if you were to train it in using those phrases.
But you would need examples of exactly that phrase.
Correct, yes, exactly.
Hi, I would like to ask why you have to add a T-step noise to the image before you feed it into the frozen diffusion model.
So we actually empirically tested sort of which internal representation gave us the best sort of features to be able to do the segmentation task on top. And we have ablation studies in the paper, and we found that sort of using sort of the last step of the diffusion model. Well, we also tried not adding noise and different stages, early stages of adding noise and large amount of noise and so on and so forth. We empirically found that this was what produced the best accuracy.
So T is fixed.
T is fixed, yes. We also actually tried an experiment where we varied it and it was learnable, and we found that it always converged towards the end of the diffusion process.
Circling back to the evaluation using the new closed semantics, right? By doing the softmax at the end, doesn't that mean that you can run into situations where irrelevant choices decrease your confidence for no reason? So imagine you have you're training on a set of cats, dogs, and I don't know, dolphins, and you decide to add open labels like bulldogs, I don't know, Shetland Terriers. Won't that just decrease your overall confidence on your label, even though it's still just a cat or a dog? Wouldn't it be better to have instead of doing a softmax, something like a similarity score, or?
Yeah, that's entirely true, and I think this is an open problem actually, and I would encourage students in the audience to perhaps consider exploring this. I think in both the works that we did, we found that sort of finding this right threshold of how to associate the text embedding to the visual embedding and sort of setting the right threshold on that, whether that be through softmax or through k-means or the closest neighbor similarity. This is the trickiest bit. What we interestingly found is that, and the reason why this comes, I think, is because it's well known that the clip encoding space where you align the text and the visual information in the clip space is not very, it's very noisy because it's trained on a lot of noisy data, right? And interestingly, we also found that depending on what the category is, if you look at distances in that space, that threshold needs to be different, ideally, for each category. So it's also category dependent. For some categories, it needs to be smaller versus larger to be able to get the correct classification. So this is definitely a weakness of sort of using the clip space. I think the future perhaps is sort of, the vision language models where you actually take vision information and align it into a large language model. Perhaps that's the way forward to get better alignment between vision and text, which seems very promising to me. But certainly that's a weakness of this sort of using this contrastive space.
I see. Thank you.
For the great talk and setting aside time to answer our audience questions. Thank you, Shalini.